picture is better. If you go around to a conference or so, you see perhaps the face that you can recognize people. So this is a work done together with Saudi and Fabio Casati. So Saudi already is now back in India, doing great stuff in India. So, concretely, what is the idea? We would like to help people model faster, model better, and what do we want to do? So we want to recommend knowledge. What knowledge? Model patterns. So the whole day here today is about patterns. We started with patterns and now we go on with the patterns. And there's a lot of knowledge, so development knowledge carried inside these patterns. And this is what we would like to, let's say, communicate to developers. Then how do we want to do it? So we really want to do this proactively. So we want to recommend. While modelers work in their modeling environment, we want to, on the fly, recommend patterns and information so that they see what's going on, and perhaps sometimes they accept one of the recommendations and they get a bunch of modeling actions for free by reusing this method. So we want to be very fast, so we want to be contextual. You do something in the typically modeling, in this case is placing a component or perhaps drawing an activity diagram, just the last action, and then we react on what you just did and we propose you something. So we want to be very fast. So in HCI there is some kind of law that if you have UI changes that are slower than 0.1 seconds, then your brain starts thinking about it. So if it's faster than this, then your brain just says, oh, I clicked here, something happened there. So they are just connected. Your brain does not get distracted. If it's slower than this, then you recognize exactly the same thing, but your brain starts thinking on a second thread. Why did this happen? And one of the key ideas we wanted, or let's say goals we had, is to do this on the fly, very fast, and below this 0.1 seconds. And finally, just recommending patterns is not satisfying, at least not to the developer one. We can still write papers about it. But the developer sees a pattern, and if he says, okay, I like it, then he would like to just use it on the fly, on the go. And this is what we do. We immediately weave the patterns into the model under development in the model account. So let's say the overall big research question is, of course, can we do it? We can do everything in IT. There's always students asking, can we do it? We can do everything. It's just a matter of time and money, right? The question is, does it really help? So if we do it, does it really help developers to either model better or model faster? Faster is, let's say, easier to evaluate. We looked a bit into the faster. The better, actually, we still would have to to test explicitly. So let's have a look at the typical pattern I have in mind. So this is, it's not web service composition, but it's kind of. Some of you may remember Yahoo Vibes. By now, discontinued, like many other of these tools, but still, it doesn't matter. The whole approach, the whole idea is just about model-driven development, models, people doing modeling actions, and we are recommending pattern inside this modeling editor. So the pattern here, for example, it's a huge mess. I wouldn't be able to redo this myself now. What does it do? It is a pattern that tells how to enrich an RSS feed with geo coordinates so that it can be automatically plotted on a Yahoo map in this case. So there are 4 components. There are some connectors. We need to know which components to select, how to connect them. There are some input fields. You need to know which parameters to set there, which parameter values. And then there are some special input fields. They start with item dot. They allow the setup of data mappings. So there's data coming in, everything that comes in here has a structure, and the item dot description, we can access the attributes of the incoming flow. So these are data mappings. And let's say a typical, in this case, data mashup or data integration pipeline. And this is the kind of knowledge we would like to harvest, find, and recommend. Where do we store them? First of all, what kind of patterns and how to store them. In our case, we identified some, let's call them basic patterns. The component co-occurrence pattern, trivial. You do this, perhaps the next component you would like to use is this other one. Then embedding pattern in Yahoo pipes, there was the possibility to embed one component in another to make cycles, for example. Then parameter value patterns, they just use select a component, there are 10 empty input fields, and now what? So what values should I put there? And we can recommend just values for these inputs. The same for data mappings. How do I map a given input flow to the parameters of the component? And finally, we have what we call the multi-component pattern. This is a particular pattern because it's just everything bigger than the others. The others are really triggered. 2 components, just input values, just data mappings, and perhaps one connector in the middle. Everything that is bigger than this does not have a predefined structure, and maybe just bigger, 3 components, 4 components, 5, and lots of parameter settings and values. We just don't know in advance. This has then some implications when we recommend the patterns, because all the patterns here at the right, we know exactly the structure, so we are very fast also in querying them. While here, we store these multi-component patterns in the knowledge base, but we don't know exactly the structure. We really need to do graph matching on the fly to find these patterns here. Okay, so we mined, in this case, patterns out of the freely available models of Yahoo pipes. At the time, it was possible to access the Yahoo pipes website and to download all the pipes they have there in the repository. So we got 970 of the most popular pipes. We chose a specific topic. I think it was about sports or news. I don't remember exactly. Then we used association rule mining, frequent item set mining, and predefined topologies, and did just traditional data mining. So we didn't really do any scientific contribution, let's say, on the mining algorithm. We applied the traditional data mining algorithms to our problem, or our problem to the mining algorithms, as you wish. And we filled this knowledge base with lots of patterns. Automatically mined patterns, essentially based on
lots of solutions, lots of
yes, these are real solutions.
Yes.
Real solutions.
Then you
so
try
we
to discover similarities.
We discovered similarities, exactly. So a pattern, exactly what I wanted to say. A pattern to qualify as a pattern, it had to statistically be recurring several times in the overall data set, in the 970 pipes. So this is the typical data mining, it's just statistical support, it's called, right? We didn't check them all, whether they actually were meaningful. So some of them, yes, we checked them, and there were some interesting things, but you know, with data mining, you get 100 results, maybe 2/3 of them are not really useful. The idea here was we would ask them, the users, to rate the patterns, or just look at the usage of the patterns. So, and in the end, good things will survive. We didn't do it in the end, so it's still something that we should do. But the idea was this one: simply just throw it out, see what happens, and what survives must be somehow good. Okay, how did we recommend? I anticipated it a little bit. So we have 3 different algorithms. Actually, it's mostly one, which is the first one. It's what we call the contextual recommendation. What does it mean? So there's the modeling editor, the developer is drawing something, and let's say he places a component into the canvas. Then this component, this last action, we call the object of our query now. This is the last component. And then we look just for all the patterns that use this component and that we can, let's say, use to expand his measure model or whatever service composition model further automatically. And this is
how far did you expand? Only to the next component?
Yeah, but it depends on the patterns we find. As said, if you have the multi-component patterns, then perhaps you get 5 or 6 components with connectors and everything inside. And we did here exact and approximate search. So the exact search for all the basic patterns, as I said, they are easy to check and to query. While we did an exact and approximate search for the multi-component pattern. It's just a more complex thing, and we said, okay, let's see. We are a bit more relaxed there with our constraints. then we have two, I would call them specializations of the contextual algorithm. We just rank them. We rank the outputs of the contextual algorithm in two different ways. The personalized one ranks the buttons retrieved with the first algorithm according to the past usage of the given user. The past usage of the components in Yahoo by the user. So we just looked at the history of the user, we checked which components knows the user we are trying to support right now, and then we gave preference to those patterns that contain these components. While for the expert algorithm, we did the same, just instead of taking the components of the user we were studying in that moment, we took kind of a reference set of experts. So we defined the cloning age index in the repository. You know, in publications, if somebody cites you 5 times and you have 5 papers, you are cited 5 times, you have an age index of 5. But in Yahoo Pipes, you could clone a pipe, meaning you just say, oh, I like the pipe, I start from this one and expand it. So we said, okay, cloning is kind of an endorsement. It's like a citation. So we identified a set of experts. We stopped once we found as many experts as were necessary to cover, let's say, all components that were present in Yahoo Pipes. It was about 50 different modeling constructs. And when we said, okay, we arrive at 50 and that's it, I don't remember. Perhaps it was about 20 or so experts and we covered all the components. So this is the difference here. Just plain textbook recommendation, ordered according to personal preferences and ordered according to how the experts use the tool. Then we created some test cases. We downloaded, again, 100 pipes models, always from the same repository. So with different users, so we had also the background, meaning the past usage of the users, of the components. And we generated about 856 test cases. So what did we do? We just took the models we found and we cut them randomly into different pieces. So if this is the model we found, we just cut it. At some point, we considered the last action here as the object, the single size object. We could go back also 2 steps, for example, that we had an object size, let's say a query size of 2 components. And the question was whether we would be able to predict the next action. So we did different cuts. And as said, we made them with object size 1, one component, object size 2. We went back 2 components. And so did different combinations of, let's say, modeling history, up to 4 in this case. Okay. What could we achieve? Performance, speed. I was talking about the 0.1 seconds of recommendation time. The prototype we did was, we will see it later, just Yahoo Pipes, the regular Yahoo Pipes that runs, or that was running in the web browser, and we extended it with a recommendation panel. So each time you went to Yahoo Pipes, with the plugin installed, you would just get a recommendation panel opening at the right side, and then it was possible to consume these recommendations. Here we did a test. It was with synthetic data. It was not exactly the same data I showed before, but here we did a test with lots of patterns in the knowledge base. Up to 1,000, we had the connector patterns, parameter value patterns, co-occurrence patterns, and the complex patterns. And then we have the total. So if you look here, the ones with the colors, the 3 here, it's kind of flat. So it's very, very fast. I forgot, I was saying, Yahoo Pipes, recommendation panel, everything is done in JavaScript inside the browser. So we had up to 1,000 of each of these patterns. And the simple patterns, ones with the known structure, they were very, very fast. So essentially, we could just neglect them. What we don't see here is below the blue cross here, there is this pink cross. So it's everything depends just on the complexity of the complex patterns. But here, this is the 0.1 seconds bar. So what we see here, this is logarithmic, I would say, up to 300 complex patterns we could manage below 0.1 seconds of recommendation, which is actually remarkable. I didn't believe it wouldn't even be possible to achieve 0.1 seconds. But it was actually definitely faster. So the simple patterns are another problem if we want to recommend them. The complex ones, they at some point grow a bit, but in the real case, we were not able to find 100 complex patterns. So it wasn't even a problem in our case. But this is based on synthetic data. So one result about the performance. And then now back to the real case study with the split we did with the models and precision and recall of the three algorithms. Just the first one here. Precision and recall. So if we have recall and precision. And here we vary the object size. So the size of the query we use. Just one component, two components, or three components, or four components. And we see here the contextual algorithm, then we have the expert algorithm, and the personalized algorithm. The blue dots are object size 1. So essentially, if we had an object size 1, we always were able to retrieve something. The precision was then depending on the ranking we performed. So with the expert algorithm, in these experiments, we really obtained 1-1. Really, really amazing. And here, the red dots is object size 2. So we looked back 2 components. And the green dots, we looked back 3 components. And the pink ones, they are really, really bad. No, we don't really know. The fact is, our components were not as big. When looking back 4 components means if we want to recommend another component, we need to have patterns of size 5. And we simply didn't have them. So we didn't have many of these components. A few were there, I think, but it's very hard to recommend in this situation because we didn't have the right data to recommend. So in these 2 cases, we looked a bit inside here. Don't try to read them. I will just summarize it. If we have just one modeling component, then we have very good performance. If we go back 2 or 3, then we really saw that we need to recommend in the recommendation panel up to at least 8 or 9 patterns so that there is a positive hit for the user. That is important when it comes to designing this recommendation panel. So we need to know one thing is just retrieving the recommendations, and other thing is understanding how many you need to show that it's actually useful. So it's not small, 8 to 9 recommendations. It depends. We will show you here now the screenshot. In this case, there's only the parameter value patterns open. It's essentially just a copy here of the component with parameter values filled. But here the idea is this is Yahoo pipes. So this is the original website. And then this is the panel we added automatically when somebody opened Yahoo pipes. And then, depending on what was going on here, we recommended the patterns. This was the first prototype we did in Trento. We called it Maya. Maya, it's a weaver word, because we weave the patterns into the model. We were looking for a cool name, and we came up with the weaver word. It makes the nest by weaving grass or whatever. And you can see we also had not only IT people, but also a designer in the group at the time. And here we didn't have a designer. Here we didn't have a designer. So this is another context. It's Apache Ray. This has nothing to do with data mashups. It's just about UI. UI components, the typical, how to say, workspace where you can add and open and close different UI widgets. And this is done was done in the Omelette project, the EU project, where we actually developed the whole research. And we tried to apply what we kind of developed first in the context of data mashups, also to these UI mashups. Where's the recommendations? Here, it was just a known widget. We just opened, we developed a known widget that somebody could place inside this Apache Ray workspace. Same thing, depending on what the user was doing in the workspace, we retrieved patterns, clicking on the pattern, opened some details, and then it could be opened into the workspace. So, user studies. I like this work because we did it from the beginning to the end. So we really have checked whether our initial hypothesis really worked. So we studied three hypotheses, and of course we were very optimistic. Bias speeds up mashup development. Okay. I should perhaps have called this just modeling or model-driven development. As said, I don't feel this has any specific attachment to mashups or to a specific tool. This can be generalized. Then development requires fewer user interactions. So if the user interaction in our case was clicks, we counted the clicks inside the modeling environment. And then development requires less thinking time. Thinking time is the time between one and another click. So as very optimistic. We did a crowdsourced user study. That is an experiment on its own, actually. Why did we do this? Because we didn't have enough Yahoo Pipes experts in our group, or usually you enroll admins in the university. Who knows Yahoo Pipes? Nobody. So we did it on Amazon Mechanical Turk, and we did, of course, an initial qualification test, so the users had to pass a set of questions, and they really had to know Yahoo Pipes, otherwise they wouldn't have known how many components can be embedded in some other component. Just if somebody wanted to fake his Yahoo Pipes knowledge, he would really have had to go to Yahoo Pipes and to study in order to know how to answer these questions. So we found some people. It took us quite a while, but we found enough people. Actually, about 30, I don't know, yeah, 30 participants that we could then split into control group and test group. So the control group, all the groups, they had to download our plugin to install it on their browser and to use Yahoo Pipes. And the control group had only just the start button and the stop button. So we just counted, we just logged the user interactions. They didn't get any recommendations. The test group, in addition to this start and stop button and to the logging, had the real recommendation and could use them. And so let's see what we found. So the development time here, we have always the control group at the left and the test group at the right. The test group, what had they to do? I mean, the modeling exercise, we gave them like half a page of text, the description, and it was detailed enough so that everybody could do it, except I think one who just abandoned the whole test, and that is not counted in the third year. But it was simple enough, detailed enough, let's say, the scenario, so that everybody could do it. And the question was really just, how fast are they? Is there everything? So in this case here, we see the test group performed about 3 times faster than the control group. They got, I don't know, what is it, 4 times less clicks. So they had to do much less in the editor, much less themselves. But the thinking time was higher. So, okay, I said we were very positive with our hypothesis. Okay, but it makes sense. First of all, who cares? Who cares if this is slow, if in the end the overall development time is anyway fast? So this just means that we introduced an overhead. And then it's actually, when we thought about it much better than when we formulated the hypothesis, we could have identified it ourselves immediately. We just wanted to make consistent formulations of the hypothesis. And then outcomes are as they are. So this just means that if there is a modeling tool, and the user is used to this modeling tool, he has one development time. We introduce also recommendations. Yeah, it's an overhead, because the user or the modeler has to also go through the recommendations and through these patterns and understand, do they make sense, should I use it, should I not use it. So it takes them a little bit more, I don't know, but it's not such a huge difference, but it takes them more thinking. But it's not much. So we retain the hypothesis about the development time and about user interactions, and we cannot accept the one about the thinking time. So this is what we did, what we get with Yahoo Pipes on Amazon Mechanical Turk. We have no idea who the users were. So we just say that's what happened. So some people in the HCI community would say, oh, horrible what you did. I spoke about this with one of the HCI people in my university, and she was actually very excited about this. we would like to deepen, let's say, the idea of crowdsourced user studies, so there's something for the future. But we did also a very traditional lab study. Actually, even better, it's not us who did it, but the partners in the project. Specifically, we headed a project, Huawei, in Shenzhen, in China. And there was T-Systems, MMS, it's a Deutsche Telekom company in Berlin. And they did the traditional lab setting. The scenario, they taught the people how to use. The test was done with the UI tool, so not with Yahoo Pipes, but with the Apache Wave tool. So they just enrolled people inside their company. But in total, 44 participants. Context is now UI, component recommendation, and the results are encouraging as well. So they kind of confirmed what we got with Yahoo Pipes. So as I said, the tool is a different tool. The people who did this study, we didn't do anything with them. We just prepared the tool for them and the recommendations. And they did the study on website. They were only able, they were testing a lot of stuff inside the project. So for our tool, they were only able to test the development time. So we don't have here the thinking time or the number of clicks. We only have the development time. But still, it's anyway very good. And they confirm what we got out of Yahoo Pipes. Only 50 minutes, but that's tough. I will just go as fast or as slow as it goes. In conclusion, we have seen that recommending and building model patterns can really make models more efficient. I mean, if it's well done, it can really we developed a concrete proof of concept of it. Now, it's not a product. Yahoo Pipes is no longer there, so you cannot even test it. Believe me. Trust me. Trust me. So, and of course, one of the key ingredients of the whole work we did are the patterns. So, you are doing patterns. We really, as I said, very naively applied standard data mining algorithms and used them straight away and said, let's see what happens. And we got something useful out of it. Yet, we were not so happy about exactly the size of the patterns. They were trivial patterns, mostly very easy, of course, when mining component parameter values, trigger, or component co-occurrence patterns. Just two components happening several times together in the models. But that's not really satisfying. We wanted a bit more. So we asked ourselves, again, for us with Carlos, allowed to see here, is the crowd able to discover meaningful, reusable model patterns? Well, if we did it with the algorithms, of course they spit out lots of add-ons if we want. But can we do something different with the crowd? I mean, it's really a paradigm shift. So one thing is, you cannot get things out with the algorithms. You go to the expert. You pay a lot of money, and the expert gives you 5 patterns. The DEIB gets 5 patterns. I saw it more than 5, but it takes years to get them out. So we tried to do this with the crowd. We said, okay, we need perhaps some human intelligence. And we said, okay, let's also forget about the statistical support. Just let's show people the models and ask them, is there anything you would like to reuse? And do you think it would make sense to reuse? And yeah, I will show you what. Then finally, is it possible to crowdsource also the quality assessment? Because as I said, with the mining algorithms, they always produce something. It's hard that they don't spit out something if the data set is big enough. The question then is it meaningful? And this is again up to the experts. Which means you sit down, you look at the pattern, you decide, does it make sense, yes or no? Here we ask, okay, first, can we use the crowd to mine, and then can we use the crowd also to self-assess the owner? So what we did very fast, crowdsourcing, more or less how it works. When you ask a huge crowd of people online to do simple tasks, you add a lot of redundancy by putting, I don't know, hundreds of the same tasks, and in the end you aggregate and you hope you get meaningful results. Very fast sum. Let me just skip this. First experiment. We took the same data set as before, more or less, exactly the same, they should actually be the same. So for the crowd experiment, we took 14 randomly picked bytes model, and then for the algorithms, we wanted to see the competition. We kept all the 900 or 1,000 models. And then we wanted to compare the number of patterns identified, the average pattern size, the distribution of the pattern size, is it all just size 2, is it all just size 3 or so, just to see if there's a variety. And of course, the crowd you have to pay. And also in the end, you want to know the cost of the whole experiment, because if the output is, yeah, each individual pattern costs you 10 euros, then you say, perhaps it works, but I don't know. I can still, for 10 euros, I can go to an expert, or I can do it myself. But if it's 1 euro, maybe there's the break even. I don't know. It depends, of course, on the work. With the crowd, you never know what happens. So you design a task, and you ask them to perform your task. But it's really, really hard to anticipate how they react to the task and the quality of the outputs you will get. There are so many factors there that affect the quality. That, yeah, the only thing you can do is you make 2, 3, 4 reasonable task designs, and you check them, and you try to understand which one works better, and then kind of you go on with them. So we designed 3 tasks, naive, really, really naive. We show just the model and ask them to click on the components that they think form a pattern inside this inside the model. Then we said, okay, we talk about mining. If we send this to some mining, whatever conference or journal, they will ask us about the support. So what if you showed the same model to more people? What if you showed 3 models instead of just 1? So we said, okay, let's do it. We asked in another task design the people to look at 3 different models, and then to tell us if they found there's something that could somehow, I don't know, be shared among these models. And then we exaggerated a little bit. We made this choose and design. We just showed them 10 different models. We said, pick the 3 that you like and tell us if there is something that these models share. Okay. And then, of course, we had the automated algorithms. So this is the basic design we used. There's the YAML bytes model. And the users, they could just click here, and this is a pattern. So in this case, it would be a pattern with 5 components, with all the parameter settings, with the 4 connectors inside. And then they could put some metadata, give it a name. The name was important. The name and the description, because we checked in the end the seriousness of the workers by comparing what they said and the name they gave to the pattern, whether it really reflected the content of the pattern. So if there was no correspondence between the text, the traditional ASDF or whatever, then we didn't consider the pattern. Perhaps it was a good pattern, but we just kicked it out because we said if it's not serious enough, let's say the description, also the pattern perhaps doesn't make sense. Okay, this is what happens. The 3 algorithms, we deployed them on Crowdflower in this case, which is another crowdsourcing platform. We got 326 people in the naive design that opened our task, 174 that really did it, and out of these 174 really did, meaning they submitted results, and out of the results we kept 42 after this manual check. We call them the valid patterns. With the random 3, where they saw 3 models, we actually, it's interesting, we got more or less always the same number of, let's say, openings of our task. But here only 17 really did it. So the others, they just abandoned it. It was likely just too complex to do. And here we kept 10 of the models. And with the choose end, we got 14 submissions and 3 models that survived. It was, that's what happened. So we were also surprised. Perhaps I should go faster here. So these are the gray bars, the machine algorithm, which was just the one we used in the first paper, with the 1,000 patterns distributed here and with the respective support. We placed the crowd patterns here at a support of 0.025 because to us it was enough. If out of the 40 models we crowdsourced, just whatever submission, meaning single submission out of 40 was already to us fine. We didn't check the support as so we placed it here. This is just to say the number of outputs we got. If you use 1,000 models with the machine algorithm, you get huge amount of models. And the crowd compared to this is of course a little contributing. But if instead, for example, you really only had 40 models because you just start up your modeling tool, then with the crowd you can actually get a significant amount of useful patterns, let's say. Here, the average size, let's go straight to this one, the distribution of the pattern sizes. So with the machine, with 1,000 patterns, you almost all the patterns are just component cohorts patterns. So this component with that component, this with that, always the same, kind of an association. If we have a smaller data set, we of course lower the threshold for accepting papers. Here the support is 0.05. We get a little bit more variety. So here, actually it seems similar. But what is very interesting is here our naive crowdsourcing experiment. The other two crowdsourcing experiment, the random 3 and the choose n, they produced similar results to the algorithm, just small variety in the size of the pattern. One naive produced very strange things. And we checked, for example, there was one pattern with 15 components. These, of course, we all checked and they made sense. So, very interesting. So, the very good thing is, yeah, with this naive algorithm, you capture a lot of domain knowledge. Because you know, a big pattern means there's a lot of knowledge that you can reuse. If we can recommend a pattern with 15 components inside that the user really wants to do it, then it's a click first component, then you get a second click on the recommendation, and you have more or less your whole model already ready. Faster than this, it's very hard to beat. So very good in this sense. About the cost, each experiment was about $17.56, and if we also count the number of patterns that we retained from these experiments, one pattern with naive had a cost of 42 cents. With random 3 it was $1.76, and with choose n we were at $5.58 for a single pattern. Okay, that perhaps not, as I said, not a production system. Good. What's this called? Quality assessment, let me be very fast, just to say, we did again 2 experiments. In individual, we asked people just rate the pattern, and in the other one, we asked them to compare 2 patterns. Which one is better? You don't need the numbers, just look here. We were not able to make an experiment where the crowd was able to produce the ratings as our experts. So we did rate each of the patterns ourselves, which is the gray bars here. And then we had different experiments with the crowd, and we were simply not able to make it. Perhaps it's our fault. We were not able to design a task that put the crowd into the condition to produce ratings like us. So in this case, we have to say we failed. So in the end, time is over. Yeah. Perhaps this is still interesting. I skipped the last paper and I talk about it. What is here? So, back here. We were not able to get good quality assessments with the crowd. So, in the end, we are back, like in the case with the machine algorithm. So, you can do some mining either with the machine or with the crowd, but in the end, you still have to look at it yourself if you really want to understand if things are good. Or, as I said before, you just dump it into the system, let it run, and depending on the usage of the patterns, in our case, things survive for now. Here we did a precision and recall again, and you can imagine the patterns, they were ranked, and we looked at the percentiles, the first 25%, the first 50%, the first 75%. And this, why did we do this? Because we saw that the first 5 or so, or as we said, the first 8 or 9 recommendations. In the first paper, I said we need to have at least 8 or 9 recommendations to test something meaningful. 8 or 9 were just not enough. So we said, okay, let's look at the 25th percentile and the 50th percentile. And at some point we were a bit embarrassed and we said, oh, let's go to the 75th percentile. You see, only here we have actually a good, good precision and recall with this crowd quality assessment experiments. It looks like a failure, but then you reverse a little bit the thinking and you find, yeah, actually the approach could still be used to filter out the worst patterns. So it means the 75th percentile, so 75% of the patterns, yeah, and they are fine, but everything what is there, so they are fine, but we could not really give meaningful value to them. But everything that is worse than these 25, perhaps we can just throw it away. And you know, also identifying the bad patterns is already something. So it's not completely an idea that we should throw away. We didn't go better into the details. So this could be used, this crowdsourcing idea with the quality assessment could be used to filter out bad patterns instead of giving ranking to the best patterns. Okay, so using suitable class designs, the crowd is able to identify meaningful patterns. And more visibility into the data set, I said the data mining idea, so providing the crowd with more visibility into the data set, giving them 3 models or 10 models, does not help at all. Actually, the more we show them, the less productive they were. And finally, so we were not able to obtain reliable quality assessment for the crowd. And yeah, I had lots of other ideas, but I will just go to the real conclusion. Yeah. So model patterns can really help if suitably recommended and used. The key problem is, of course, finding good patterns. And there are many ways of doing it. So you really go through the literature in time or observe people. Exactly. So it's impressive when I saw the talk this morning. It reminded me very much about doing a survey paper, because we just closed a survey paper on quality control in crowdsourcing just by chance. And that's actually what you do. You go through the literature or to observe, and you don't just want to tell this paper did this, the paper did that, this other paper did this other. No, you want to identify the patterns. That's where the knowledge is. That's where the knowledge is. And I'm a reviewer right now of some survey paper that was submitted to some transaction journal, and I'm struggling to teach these people, the authors, that nobody cares about how many papers have been submitted in a specific conference, because they count. They say, we do a systematic mapping. There are 5 papers talk about this and 5 papers talk about that. And second round already, I tried to tell them, look, people don't want to read 5 papers did this and 6 papers did that. You need to explain what they solved and what the problem is and how they solve it. So there will be exactly the patterns again. So doing the right survey teaches you patterns if it's by now. So finding them is the really, really tricky thing. And what is the crowd may be a viable alternative. As you see, I'm trying to inject some human computation, let's say, in traditional mining contexts, because sometimes the human knows a bit more. As we've seen with the naive mining algorithm, we got very, very interesting big patterns that we would never have found with the machine. Okay.
Although interesting.
Okay, thank you. So, as you already have the first question.
Thank you. Only the comment, so traditionally patterns have been found by human beings.
Yes, of course.
Right? So you did read this cover that it's a good idea to trust human beings to discover patterns.
Yes, exactly. Yeah. Traditionally, human beings were computers. Yes.
But the traditional patterns are really identified by human beings. Right? And only recently.
In your case, it's experts.
Correct. Yes.
Together with your team, you are the experts.
No,
yes.
What I mean is also in other areas, in architecture, in drawings, and something like that.
Definitely. This is just one difference, perhaps. In your case, we talk about experts, the architects, and they identify the people better. Here we try to do it with the crowd. So the only expertise.
So what you're saying is Okay.
The only expertise we ask.
Can take that.
Sorry?
If you have a lot of naive users, you don't need experts. That's what you're saying.
Yes.
Okay. Yes. True.
Yes.
Yeah.
So this is kind of the takeaway. Yeah.
Okay, we still have time for one or two questions.
When you looked at the pipes, yeah, and you wanted to find out what are the associations in there, type 1, 2, 3, and how often it shows up with frequent items that mining.
Yeah.
How did you decide on whether one of those nodes in one of those pipes, yeah? So you have pipes where you have operations and then you pipe the data to the next operation. When are the two operations the same?
The same. Oh, there's one. Yeah, exactly the same is not so trivial. There are different levels.
No, that was my question. What is your definition of being the same node?
Our definition. Okay, so I'm 100% sure about the first part of my answer, and so sure about the second part.
Okay.
So in YAML pipes, it's a modeling tool where there are about 54, 56 different components.
Okay.
So you can distinguish them very well. So in business process modeling, for example, in BPMN, you have the tasks, but then you can write whatever label you want. So there you have a huge problem. Here we just had a limited alphabet, let's say, of components, and it was easy to understand. These two components, component X was used together with component Y because they have static names and they are all the same names in all the models. Then of course they have parameter settings, and I don't know exactly at what level we stopped. Perhaps, as I say, perhaps only at the level of the components. This for sure.
Yeah.
Perhaps in some of the experiments, we also filtered based on some parameters, like the most important parameter. When you access an RSS feed, like the URL. But I don't remind her about it. So, yeah.
Okay, so no more questions. Thank you again. The next talk is given by Tia Sayed from Philips Research in Eindhoven, and